Alright, let's quickly recap what we did in the last video. In the last video we were talking about dampened simple harmonic motion, and we were able to get this differential equation here. Second derivative of x plus gamma times the first derivative plus omega naught squared times x is equal to 0. Where gamma is our measure of our damping force, and omega naught squared is kind of like our natural frequency squared. And the reason we say natural frequency is that would be the frequency if there were no damping forces. So we had this differential equation and we tried to solve it. We got this characteristic equation and we tried to solve for r, and we found that r is equal to negative gamma plus or minus the square root of gamma squared minus 4 times omega naught squared, all divided by 2. So before we proceed, let's just do one quick simplification. Essentially, I'm just going to factor out a 4 from underneath this radical sign. So we get that r is equal to negative gamma plus or minus the square root of 4 times the square root of gamma squared over 4 minus omega naught squared. All of that over 2. Now the reason why I did that is now we can just divide each term by 2, and we get that r is equal to negative gamma over 2 plus or minus this radical 4 term cancels out with a 2, so we're left with the square root of gamma squared over 4 minus omega naught squared. But as we said in the last video, we're left in a bit of a pickle, because we don't know, the relative sizes of these two terms underneath the radical sign. There may be some cases where there's much more damping, and there may be other cases where there's less damping, in which case underneath this radical sign can be positive or negative. And we said that we have to take a look at each case individually. So we're going to start off by taking a look at what we like to call the underdamped, or the lightly damped case. And that's going to be the case where the restoring force is going to be much greater than the damping force. So gamma squared divided by 4, that's going to be less than omega naught squared, which means that this term here is going to be greater than this term here, so under the radical sign we're going to have a negative value. If we're going to have a negative value, let's just factor out a negative 1 right now. So we can say that r is equal to negative gamma over 2 plus or minus I times, now we factored out a negative 1, so this becomes positive omega naught squared, and this becomes negative gamma squared over 4. And now we know that this is greater than this, so this is a legal square root sign, we can say. And since omega naught squared and gamma are just constants, this whole entire thing is just one messy constant. So we found our two values of r. Negative gamma over 2 plus this messy constant, and negative gamma over 2 minus this messy constant. So we can plug our two roots into the general form of our solution. So we get that our two solutions are e to the negative gamma over 2 plus I times the square root of omega naught squared minus gamma squared over 4, all of that times t, and e raised to the negative gamma over 2 minus I times the square root of omega naught squared minus gamma squared over 4 times time. So here are our two solutions, and we know that the general solution is going to be a linear combination. So we can say that x is equal to some constant c1 times the first solution, plus another constant c2 times the second solution. So we found the general solution. The trouble is, the way we have it written now looks really ghastly. Let's try and see if we can simplify this in a way that looks much more intuitive. So the first thing we can do is we can factor out a t term into all the exponents. And notice that each of these two terms have an e raised to the negative gamma over 2 term. So we can factor that out. And we can simplify it and get that x is equal to e to the negative gamma over 2t times c1 e to the I square root of omega naught squared minus gamma squared over 4 times time, plus c2 e to the negative I square root of omega naught squared minus gamma squared over 4 times time. So now we have like a sum of two complex exponentials. So we can simplify this up by using our Euler's formula. E to the I theta, that's just cosine of theta plus I sine theta, where this giant thing can be our theta value. And if we do that, we get a sum of sines and cosines, and we can group all the cosines together, and we can group all the sines together. And if we were to do it all out, we'd find that x is equal to e to the negative gamma over 2t times a new constant a times cosine of the square root of omega naught squared minus gamma squared over 4 times time, plus another constant b times sine of the square root of omega naught squared minus gamma squared over 4 times time. These two forms are interchangeable. I didn't really want to work out all the steps considering we did that, and I want to say about like 2 videos or so ago. But if you'd like, if you're not too sure how I got this, essentially I just plugged in Euler's formula here and here, and I grouped all the cosines together and relabeled the constants in front. So you can get this from that if you, I think, define A as C1 plus C2, and if you define B as I times C1 minus C2. But like I said, these two forms are interchangeable. So what do we have here? This kind of looks like what we had for the solution for the simple harmonic motion. A times cosine plus b times sine. And it may be a bit more clear if we define omega as the square root of omega naught squared minus gamma squared over 4. If that's the case, then we get that x is equal to e to the negative gamma over 2t times a cosine omega t plus b sine omega t. And this basically does look like our solution for simple harmonic motion, except this time modified by something. In fact, we can go one step further if you like. We can even rewrite this parenthesis term in amplitude phase form. So we can say that x is equal to e to the negative gamma over 2t times an amplitude, say c, times cosine of omega t minus v. So here's our general solution, just in a much more intuitive and workable form. It's the same exact thing as this, just slightly easier to look at. Now I'm pushing on time a bit, so I might continue this in the next video. Essentially, we're now going to be talking about, now that we've found the solution, what is this really saying about the system? So I'll hopefully see you soon.